Isaac, I'm sorry, I'm having problems with the connection. Can you hear me now, people? Can you hear me? Somebody?
Yes, doctor.
Yes, sir.
Doctor,
Yep.
I have a question. The shear force is not positive upwards.
Yeah, that's why here, if I need this shear force pointing downward, that way in this area, it is negative.
Correct.
In this area, yeah, from here, from the left end, okay. Let me see my pointer. What is my pointer here? It's my pointer. Okay. From the left end until here, shear force is negative. And from here to here, shear force is positive. Okay, so I'm going to analyze in a region where the shear force is positive. Did I answer your issue, your problem?
Yes, doctor, thank you.
No problem, no problem. Okay, so that's the problem that we're going to be analyzing, okay? So up here, let me review, before we go on, why don't we review the formulations that we can apply in order to analyze this problem, okay? Let me go back here, okay? This is the formulation that we want to analyze, okay? So I have this difference in force. This is axial force on the sector, right? And that means that if we consider this Fs and we consider this cut,
Doctor, I don't listen you.
cooperate with us. Okay, so we're going to restart. Let me close everything because see my screen, people?
Yes, doctor.
Can you see it?
Yes, doctor, but not full screen.
Yes.
Oh, no.
Better.
Okay, so this is the situation, okay? So this is the cause of our problem. There is no axial equilibrium. And this is the rate of change of the axial force on a sector. And this rate of change is what we call the shear flow. Depends on the shear force, inertia, and the first moment of the sector, okay? And of course, if we want to have equilibrium, this is the way that we're going to analyze. This is very interesting, people. Let me insist here, okay? This is the neutral axis, and this is the direction where we are making the cut. So this phase down here is a negative phase, right? Because the normal is pointing in the opposite direction which defines the position of this cut, right? So this is a negative. So that means that the positive shear points in the negative x direction. And this is what I'm showing you here. This is very important because we need to consider the direction to have equilibrium, okay? And the rest is easy, right? We have a force, EF, that we were able to evaluate. This is the force. In the opposite direction, because points to the left, this is the force in the cut, and this is the parameter that we want to determine, B dx. It is very important that we remember this is a limitation of this formulation, right? Okay, so we're saying that the thickness when we make the cut is small. If this is not true, then we have to consider the variation of tau. So we will do an integration, okay, in the z direction. But the problem is that in that case, we have to include more information because we have no idea of the variation, right? So the only way we can apply this directly is to assume that B is small. If this is small, then we can say that the variation in this direction, this is the z direction, okay, is small. And we can say that the force on this is simply the average value of tau times the area, which is B dx, okay? That's easy. We cancel the dx's and we say that the tau is equal to Q over B. Now, this is the reason why we call Q shear flow, okay? You can see that Q depends on this first moment, and the first moment is the result of integration, okay? So when you have two branches in a section, and we will see that in a minute in an example, the integration of this parameter, the first moment, adds up in a point of connection. But that's this. And you can see there is certain continuity in that. And that's why we call it shear flow, because it's like having two pipes which are connecting themselves. But in the case of the shear stress, we have to divide that. We have this type of continuity. We have to divide it by B. And we can have, for example, difference in thickness in the web than in the flanges. So when this is continuous, this is not. We can have jumps. And that's why usually what we do is we work with the shear flow. And at the end, when you want to make the calculation or to calculate the shear stress, what you do is you consider a certain position, okay? From the plot, from the sketch, you get the shear flow, and you simply divide that by the thickness in that point, and you get the shear stress. And we do this because we can check that our calculations are correct, because this parameter, the first moment, is a continuous one. That's the explanation, okay? So this is the formulations that we're going to be doing. And the main idea of these people is that we need to have all the time any piece of our beam, we need to have it in equilibrium, okay? Static equilibrium, okay? So if you have a certain segment or a certain sector of the beam, any sector has to be, any segment has to be in equilibrium, okay? That's the main thing that we have to have in our mind. Every time we analyze any piece of the beam, that piece has to be in equilibrium, okay? Now, let's go on. Just last night, I posted, okay, pieces of this section, okay? And that's what we are going to be doing this morning, okay? So if you had the time last night to view this, fine, okay? Otherwise, I ask you to be alert because in some cases you can find this a little bit confusing, but it is not. It's just there has to be equilibrium in the X direction. One more time, equilibrium in the X direction. Okay, so this is example we are going to be analyzing, and we're going to consider the section, okay? And we're going to be doing cuts at different points of the section, okay? So this is the section again. Let's assume, as you can see here, that the shear force is positive, right? Okay, now we have cuts, as you can see here, A, B, C, and down here, D. Now, everybody right now, consider this piece, okay, this piece. And this corresponds to the cut A that you can see here. It's in the upper flange on the left side, okay? Now, let's draw on this side, let's draw the shear stress, okay? Here, I'm going to write it like this. This is the rest of this of the beam, okay? I'm going to analyze only from this cut to the left, okay? Now, let me change color because that's there. So, as you can see here, see, down here is the neutral axis. So, we go up, 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 and we go like this. So, this is the position S, okay? So, in this direction, okay, that's the positive S. So that means that this is a positive or negative phase. This phase is positive or negative. Let me need it.
It's negative, doctor.
It's negative or positive? It's negative. Okay, so if it is negative, that's correct. It is negative. So the positive shear stress, let me include here. Let me include here. So that's the x-axis. Now, if this is a negative phase, okay, the shear stress will point in the positive or in the negative direction, x direction. Anybody? Anybody? The positive shear stress here will be pointing in the positive or in the negative x direction.
Maybe in the negative direction?
Exactly, exactly. So that's my tau. And finally, what are going to be the sub-indices of this tau? What are the sub-indices? Sx. Let me erase this because we are going to can get confused. Okay. So that's the situation right now. That's the situation right now. Okay, now let's go on and deduce the expression for tau. Now, let me write down here, tau, in general, xs, or sx, I'm sorry. Jesus, people, please. I have to stop the class because somebody's bugging me. Don't write on the screen, people, come on. So it's V of x, Q, S, divided by the inertia, and B. We consider a cut here. So for any any sector of this section, V is positive, right? I sub C, it's always positive. And this is the thickness, which is always positive. So all of this is positive, right? Now, in this case, okay, Q of S, we are in the upper part, it's always positive because the Y average for this is the sector, right? This is the sector. So for this sector, we are above the neutral axis. So Y average is positive. So in this case, this is also positive. So all of this will produce a tau Fs Sx positive. So that's the correct shear stress on this cut, okay, AA. Okay, now, if I ask you to draw, people, be careful. If I ask you to draw tau XS, okay, on this face here, what will you draw? In the positive S or in the negative S? Anybody? Anybody here? Tau Sx will be to the right or to the left? Anybody, please.
To the left,
Yes. Why you say that?
because we can see like the shear forces go upward and then open to each side.
The reason is because this is equal to tau Sx. So if tau points in that direction, then you have to have xs in the other direction. Remember, let me write up here. Remember, this is solid mechanics. If this is tau, this is tau. Okay, if this is tau xy, this is tau yx. So the 2 points towards the same corner. Okay, if you have something like this, you have something like this. The 2 arrows point to the same corner. So in this case, the arrow points in that direction. So in here, in this phase, the tau has to point in this direction. So this is tau Sx, xs. Okay? Now, in a minute, I will explain why this makes sense. People, you draw this in here. You do the same analysis, but considering a cut B. Okay? So this cut start, we have something like this. This is the web, okay? This is the neutral axis, and this is the x-axis. And I want you to analyze the shear stress on this cut and also on the other side of the cut XS. You tell me, points in that direction or in the positive X. And on here, points to the right or to the left. Call somebody to explain your answer. I'll give you a couple of minutes. So if you think you have the correct answer, raise your hand, people, so I can call you and we can go on with the class. But everybody, I need everybody to do an effort, okay, in trying to answer this question. On this card, BB, okay, on this card, the shear stress on this card will point in the positive or in the negative X direction. And then from there, we can draw the shear stress on the cut of the section. And I want you to tell me that if that stress, you expect it to point to the right or to the left. Mr. Ortega, are you there, Mr. Ortega? Can you hear me?
Yes, doctor. Good morning.
Okay. So tell me, see, right now, see, you are integrated from here until the end. So this is the X direction, okay? So in here, that's going to be a tau Sx. Please tell me, this tau Sx will point in the positive or in the negative X direction?
In the positive,
Positive.
in the positive direction.
So you say it points in this direction,
Yes.
okay? Is that correct? Okay. Let me ask somebody, Mr. Kimi, do you agree? Mr. Kimi, do you agree with that? Mr. Kimi, do you agree with that? Here. Mr. Kimi,
Hi.
do you agree
Morning.
with that? Is this the correct direction for tau Sx on this cut?
Yes.
Do you agree with that? Okay. Let's ask somebody, Miss Arechua. Miss Arechua. Do you agree with this? Is this correct, Miss Arechua?
Good morning, Miss Doctor. I think that is in negative X
Yeah. Why you say that?
by the structure of the I section and the direction of the X.
Yeah, the direction of this. That's the correct answer. That's the correct. Let's see. Now, if this is the direction of the cut, okay, because that defines the sector. This is the sector that we're analyzing, okay? This is a negative phase, okay? So this is a negative, the phase is negative. So in a negative phase, I would say that is positive. So this is tau Sx. And this has to be positive because again, to evaluate this, we have the same formulation. So in the open position, Q of S is also positive because you can see that the distance, the vertical distance from the neutral axis to the centroid of this sector is positive. So all of this will give us a tau Sx positive. So that's positive. And again, in this cut, we're going to have this is going to be tau Xs. Okay, so in here, this stress Xs points to the left, and on the other side of the flange, the same stress points to the right. Okay, the values, we can evaluate them later, but right now, we are only interested in the direction. Okay, now, so we have done so far the analysis in cuts A and B. Okay, see, we have done this, we have done that. Let's analyze cut C, which is on the web, the next page. Here, this is the analysis at cut C. Okay, so this is a cut C, you see here, that's a cut C on the web. Okay, so this is X axis in the positive direction, this is Y axis, and the cut is defined at position Y here. Okay, now on this crossed area, okay, the tau, what are going to be the sub-indices on this cut? Miss Avilés, on this cut, what are going to be the sub-indices for this, for the tau on this cut, on the cross area?
Is YX.
Exactly, YX. So Y because it's normal to that, and X because it points in the X direction. Okay, and Miss Avilés, this area here, the cross area that I'm pointing here, this area, it is positive or negative phase? Positive or negative phase?
The negative phase.
Yes. So You have to have a positive in that direction. So that's going to be tau yx. And finally, on the web, see, we're going to have in the vertical direction, we're going to have tau x y. People, is there any questions about this? Any questions about this, people? Questions?
Doctor, for me, it's not so clear about the negative, why you consider the negative phase when you point S over left or S over right.
Let me try to draw. I'm going to draw a profile, okay? So this is the flange. This is the web, and this is the lower flange. Okay? This is the x-axis, and this is the y-axis. Okay? So we're making a cut here. So, and this here corresponds to the cross area that I'm drawing here. So I'm going in this direction, that's a positive y. So that's the normal to this is pointing in the negative y direction. That's why this is a negative phase. Okay, so in this negative phase, okay, that's going to be tau xy, not yx, the shear that is going to be working on it.
So in the flange, when we consider that the S points over right is negative because it points with
Exactly.
a different sign to the S.
Exactly. Here, that's what we started clearly saying. Okay, remember, let me go back. Here, we said we're going to define a sector, right? And the sector was defined considering a certain cut, in this case at position Y, and we went up until an open phase, because in the open phase, we know that the shear stress is null. So what we are going, I mean, I couldn't say that because at that time we didn't have the formulation, but the idea was to obtain a value for tau at the level of the cut. Okay, so since we have only one equation, we could have only one unknown. That's why we started here and we went up to this point, h/2, where we know that the shear stress in here is 0. So we go in this direction from the cut until the end. That's the key of this analysis.
Okay, thank you, Doctor.
No problem, no problem. If I didn't answer, I'll try to explain it to you in another way, but hopefully you said that you got it, okay? Anybody else, please? Anybody else?
Doctor, I am a little confused about how I know.
Please, the person who is speaking, I cannot hear you clearly. Would you please try to get closer to your microphone, please?
Hello, can you hear me?
No, I cannot hear you clearly. Remember, I'm 65 years old.
No.
Okay, go on.
I'm a little confused about how do I know when a phase is negative or positive and the direction of tau. I still don't get it.
Okay, let me, okay. Let me try to open a new, give me a second, okay? Give me a second. I'm trying to open a new page. So I'll try to, okay, can you see my screen? Full screen, people?
Full no, doctor.
Just the screen.
Now?
Now, yes.
Okay, thank you. So, okay. When we, unfortunately, I couldn't, let's do our best. Okay. When we have a beam, okay? Okay, we say this is the beam, okay? This is the X direction, right? If we make a cut here, we consider this part, okay? That's the X direction, and that's a normal outside, okay? From the segment that we're analyzing. And this points in the same sense as this one. So we said this is a positive phase. But we could also consider the other side, okay? So I'm going to draw here. That's the other side of the beam, okay? This is the X direction because that doesn't change. But now the normal pointing outside the segment points to in the negative X direction. So this is a negative phase, okay? Now, we agree, okay? This was the convention that we employed. And we said, in the positive phase, this is a positive shear force. In the negative phase, this is a positive shear force, okay? Similarly, we can apply that to the case of stresses. Okay, so if we have a plate, for example, this is a plate now, okay? Let's make a cut like this, and we're going to analyze this area here. So we have, let me go. This is X, this is Y. Let's analyze this piece here, no, this piece here. So I have this, okay, this piece is this one here. Now, this cut is perpendicular to the x-axis. The person who is asking me, question, is this a positive X cut or a negative cut?
Positive.
Exactly. So this is positive phase. And now comes the question. This one here is a positive or negative cut, Y cut. People, this is a Y direction. This is a normal.
Negative.
Exactly. It's a negative phase. Now, on this side, let me change color. Now I'm going to explain it using or apply it not to shear force, but to stresses. Okay. Now here, if I have a stress, normal stress, which points to the right, okay? And this is going to call it, or we're going to call it positive. But again, we could also also have stresses, shear stresses, okay? So on this side, we could have tau. Okay, now, this is a positive phase, okay? Now, the positive normal stress tries to pull it, tries to elongate it. And the positive shear stress will be, since this is a positive phase, will be pointing in the positive direction. So this is tau x1. Why? Because that's the convention. If we have in this positive cut a shear stress which points upward, we call it positive. Okay, that's the convention that we use. Now, the opposite here, this is a negative phase, right? In the negative phase, to be, let me put this positive. In the negative phase, okay, the positive shear stress will point in the negative x direction. Okay, so that's the negative. And this is going to be yx. And this is also positive. And you see, as I was saying before, that if you start from here, this one here tries to rotate in this direction, and this other here will try to make you rotate in that direction. The two cancel each other, and that's why the two have to be equal for this differential element to be in equilibrium. Okay? I don't know if
Yes.
I answered your concern.
Yes.
Yes? What's your name, please?
Hidrobo. Esaú.
Oh, okay, good. Please, if I didn't really explain it to you, you still have a doubt, ask me again. I'll try to answer as the best I can, okay? Did I really explain it to you, Mr. Hidrobo? Did you understand it? Okay,
Yes,
good.
I understand.
Okay, good. I'm really glad because that's my job. Okay, so that's why it's so important to try to check the direction where we are analyzing our defining our sectors. Okay. Okay. Now let's go. This is very interesting, people. Since it's 8:01. Let's do this. Okay. Let's take a break, 5-minute break. But in the break, I want you to take a quick look at this. Okay. And the idea is that you put in your mind the segment that, or the sector that you want to be in equilibrium. Okay. Have in your mind the sector that you have to have in equilibrium. Okay. And when we return, we will analyze this. And then you can see that, let me go back. Shoot. Here, okay, I have this, the stress in here. I have the stress in here. I have the stress in here. So we can more or less have a general idea of the distribution of the shear stress on the section. That is something which is we were looking for. Okay, so let's take a break, 5-minute break, and please think about this. And the first thing I want you to think is, what is the segment that I want to be in equilibrium? Okay, the segment that I want to be in equilibrium. Okay, let's take a break, 5-minute break, because my throat needs a rest. Isaac, would you please stop the recording?